All right, let's add some vectors together. So this roughly follows sections 3.2 and 3.3 in the book. And the techniques that we're going to use here, we're going to be using a lot once we get to talking about forces. And so it's good to have a good handle on how we're doing things. So, sort of briefly going over what a vector is, we have some defined coordinate system. And for the moment, I'm going to start just by assuming this is a position vector, but the techniques for vector addition will work the same no matter what type of vector we have. And so when we talk about a vector, we're talking about a quantity that has a magnitude and a direction. And so we could think of that as starting from some origin, a vector points from one point to some other point, and it has a given length. And the way that we can often quantify this, so let's say this is a position vector, I'll call this R1, is in terms of its components, which for the moment I can just think of, that should be a Y, I can think of as giving the X and Y coordinates of this point up here. So we know how to plot numbers in the plane, and so if we think of a vector as stretching from the origin at 0, 0 out to this point here, then we can completely quantify this vector in terms of this ordered pair of numbers. And let's say that this particular vector, again, the other thing that we will be using often is the fact that we will draw these as a vector being the hypotenuse of a right triangle, and then our components are going to be the legs of that triangle, and then that of course allows us to do that is going to allow us to do trigonometry to relate all of these things. And so let's say we have this vector here, and if I think about this as directions sort of north, south, east, west, then let's say due east is my positive x direction and due north is my positive y direction. And let's say that this vector R1 represents going 16 meters due east, so that would be 16 meters in the x direction, and then 12 meters in the y direction. So, in other words, my vector R1, I can say, is equal to my x component, which is 16, my y component, which is 12, and we'll keep the units on the outside. So this completely specifies this vector. Now, the other way I can do it is with a measure of its magnitude and its direction. So that's the other way. That's how we defined a vector in the first place. A vector is something that has a magnitude and a direction. So when we're talking about this picture of a vector as an arrow, then the magnitude is going to be the length of that vector, and the direction is going to be an angle. And so we'll have to be careful about how we define this angle. Notice I've already snuck in where this angle here, so we're writing it as an angle counterclockwise from the positive x-axis. And that is typically how we will define these angles. So notice that in doing this, I've set this up as a right triangle. So if we want to find the magnitude of this vector, we'll often denote that with an absolute value symbol, and that is always going to represent the length, or sometimes we'll just write it as the same character but without this little vector hat. Right, we have this little arrow on top that represents that it's a vector, so we'll take that off. But otherwise, we just have Pythagorean theorem on this triangle here. So R1 will be x1 squared plus y1 squared, or square root of 16 meters squared plus 12 meters squared, which I have cleverly chosen things so that that is exactly 20 meters. This is in fact just a scaled up version of a 3, 4, 5 right triangle. So given the two components, I can do this to find the magnitude. Then I can also find this angle then by choosing a trig function and writing that angle in terms of either the legs or the hypotenuse. The method that we typically see in the book is one that only relies upon knowing the components. And what we'll do is we'll write down the tangent of this angle theta 1, and that's going to be equal to the opposite over the hypotenuse. So just as a note, all of these formulas that we're going to see assume that we are defining this angle relative to the positive x-axis in a counterclockwise sense. If we define the angle in a different way, then we're going to have a different formula. And we'll see as we go through different problems how that's going to come into play. But here, if I'm then solving for theta 1, I then have to take the inverse tangent of y1 over x1. So inverse tangent of y, which is going to be 12 meters divided by 16 meters. Notice that I have plugged in those quantities with units, but I have meters divided by meters, my fancy red pen, and those units are always going to cancel out. The second thing is that make sure that when we do trig that we are in degree mode using our fancy scientific calculators. Sort of until further notice, we will generally always be doing things in terms of degrees, just because most people think in terms of degrees rather than radians. And so this angle here, this angle theta 1 is 36.9 degrees, again, which is output from our calculator. And if we have this picture here, we can write this as being counterclockwise from the positive x-axis, or since we're also writing this in terms of the cardinal directions, this is equivalent to saying it is north of east, meaning we start east, which is our positive x direction, we move towards the north, that's the counterclockwise direction. So either of these methods, we can either say that R1 is equal to these components of 16 and 12 in this coordinate system, or we can say that R1 has a magnitude of 20 meters in a direction of 36.9 degrees northeast. So either one of those is completely sufficient to denote the vector. And notice both of them involve two pieces of information. I have my two components for the component version, and then I have magnitude and direction for the angular version. And so now, when we get into working with actual vector addition, we really can just think of this as an old-timey pirate treasure map, where, again, even if our vectors we're working with aren't position vectors, I imagine adding them together as if I were following the directions for one of them, and then immediately from that point follow it for the other one. So let's say we had a treasure map that said our first displacement we're going to make, R1, is equal to, I'm going to use the same vector as up here, meaning it's going to be positive 16 meters in the x direction, positive 12 meters in the y direction. So I just automatically know how that's going to work. And then my second displacement vector, R2, I'm going to write in terms of magnitude and direction, because these were very mathematically inclined pirates. So that's going to have a length of 15 meters, but it's going to be at 45 degrees north of west, meaning that relative to where we are at that point, we're going to walk 15 meters in a direction 45 degrees north of west. So I'm going to first graphically show what this looks like. Like we already know from up here that this is what our R1 is going to look like. And so I will redraw that down here just so I can have this handy. And so if I draw my new set of coordinate axes, and now I'm going to include all of the directions. So plus x is east, plus y is north, minus x is west, and then minus y is going to be south. So my first displacement vector, this r1, let me draw like this. In other words, this was 16 meters this way and 12 meters this way. So this is r1. Then, in order to get the proper displacement, we're going to say, well, from that point, we're then going to walk 15 meters in a direction 45 degrees north of west, which means that we imagine sort of drawing a brand new set of coordinate axes at that location, and then I'm going to create a vector that's 15 units long at 45 degrees north of west. So again, coming back to these directions here, west is this way, north is this way, so I'm looking at something that's going to be in this quadrant, and it's 45 degrees, so that makes it easy to draw. It's going to have a length of 15 meters. I know this has a length of 20, so this should be a little bit shorter. Again, I'm not busting out the ruler or protractor here, so I'm told that is 15 meters, that is 45 degrees. So the action of adding these two vectors together, this is what we call the head-to-tail method. Head to tail. Where when I'm adding vectors together, I take the tail of one vector, I put it at the head of the other vector, and then my net displacement, I go from the end of one vector to the head of the other. So my r total, which I'll just call r, is going to be the vector that stretches from there to there, meaning that compared to where I originally started, where do I end up after undergoing these two displacements? So, and so there's a couple different ways that we can go about this. Notice if we were really careful with drawing our lengths and drawing our angles, if we had a protractor, we can then just use a ruler to physically measure this length and physically measure this angle. But we're not going to do that. We could also notice this forms a triangle. It's not a right triangle, but it's still a triangle. So again, our options are ruler and protractor. No, I don't want to do that. The other option is using laws of trig, like the law of sines or the law of cosines. And again, this sort of just depends upon how comfortable you feel using those. If it's been a long time since you've gone through trig and don't really remember and not sure how to use them, then we're going to be using a different method anyway. That method will work if we're just looking at adding two vectors to get a third, because that always forms a triangle. It's not going to work if we're talking about adding more than one vector. So what we are then going to focus on is the component method for adding these vectors together. And how the component method works is if I have a vector expression, so this is what I'm saying. I'm saying my overall vector r is equal to r1 plus r2. So that's the vector addition that we're doing here. The component method says that whatever happens here is also going to happen for the x and the y components of our vectors, meaning that once I find, this should be r1y plus r2y, once I find the components for each of these vectors, then I can just add the components together, and that's going to give me the components of my overall vector. And then, if I need to, I can go back, find the magnitude, find the direction, using the inverse tangent and using Pythagorean theorem. So, we've already determined the components of our vector r1. We did that above. So r1 is equal to 16 and 12 meters. So we already have those numbers. Now we have to find the components of our vector r2. Now notice when I drew it up here, I said, well, I'm going to pretend there's another little set of axes there. But I'm just interested in components, then coordinate systems are free. I'll just draw its own set of axes, and I'll redraw my vector over here. And we said this was 15 meters, and this was 45 degrees. Now, when we go to find the components, we're going to do something sort of the opposite of what we did up here. Here we had the components, we used trig to find the angle and magnitude. Here we have the angle, and we need to find the components. And notice that I would have an x component, r2x, and a y component, r2y. I said earlier we have to be careful about how we define this angle. Because notice, because my vector is pointing up and to the left, my x component here should be negative, but my y component here should be positive. The other thing is that in the textbook they give formulas like, a is equal to, I guess I could just write it out. So from the book had formulas that said my ax is equal to a times cosine theta, and that ay is equal to a times the sine of theta. These work only if my theta is measured in a direction counterclockwise from the positive x-axis. And only if we measure the angle that way. If we're not measuring the angle that way, then we need to have different formulas, and we need to make sure that our signs are correct. So there's two ways we can go about this. If I look at this triangle over here, and I know I have this 45-degree angle, I just know that my x component will be negative, y component will be positive. I can stick in those components by hand, meaning I can just say that r1x will be equal to negative 15 meters times the cosine of 45 degrees, right? Because my x component is still along those directions. And if I plug that in, that gives approximately negative 10.6 meters. And then my r1y will be equal to positive 15 meters times the sine of 45, and since sine of 45 is equal to cosine of 45, that's also equal to 10.6, except now that is positive, meaning that my r2 I can write as negative 10.6, positive 10.6 meters. Notice that I had to know that I used a different formula. I had to put in an equation, I had to put in the signs by hand. I still could use these book formulas as long as I define a different theta that's counterclockwise from the positive x-axis, meaning that for this vector here, that would have to be this angle right there. Notice that this is going to give us angles that are greater than 90 degrees. And in particular, this is going to be a 135-degree angle. So if we did things that way, notice that if I plug in my quantities, a here would be 15 meters times the cosine of 135. Okay, give it a shot on your calculator. It is also going to give you negative 10.6, meaning that the sign is automatically determined when I have my angle relative to the counterclockwise from the plus x direction. And ay, 15 times the sine of 135, again, gives me the proper sign, positive 10.6. So depending upon which method works better for you, just take note of what direction these vectors are pointing. So then, when we want to, pardon me as I move things around, then if we want to determine the components of our final vector, then coming back to what we wrote up here, I'm just going to add the components together. My rx will be r1x, which is 16. My r2x will be negative 10.6, so that's going to give me a positive 5.4 meters. My ry is going to be positive 12 plus a 10.6. That's r2y. That gives me positive 22.6 meters. So those are the components. So if my problem was saying what are the components of the resultant vector, this would be positive 5.4 and direction. So now we again are going to go components. We're going to do this up here when we were looking for the magnitude and direction of that vector. So coming back down here, In other words, my new vector, again, I'll give it its own little coordinate system. It goes 5.4 units in the x direction. It's going to go 22.6 units in the y direction. My hypotenuse is going to stretch that way. So I've got some length r, I've got some angle theta. And again, I've drawn this, again, counterclockwise relative to the positive x-axis. So Pythagorean theorem, my magnitude of r is equal to square root of 5.4 squared plus 22.6 squared, and that is going to give me a magnitude of 23.2 meters. And then my angle theta, notice that since I have a positive y, a positive x, this is the same situation. My theta is going to be the inverse tangent of my y component, 22.6 divided by 5.4, or 76.6 degrees. And so my overall vector r, I can then also write as 23.2 meters at an angle of 76.6 degrees counterclockwise, positive x, or in order to find that treasure, 76.6 degrees north.